So in our previous test, we saw that when our WAN paths are equal, both the Talari and the Peplink are able to aggregate the bandwidth together for a single flow and get nearly all of the bandwidth out of both of the network paths. We did observe that when the Peplink is fully utilizing both links, he appears to induce some latency, and we noticed that our ping times would vary greatly, up to like 3 times the actual round trip. And he also seemed to induce some packet loss that he was also measuring. Whereas the Talari, consistently the ping stayed the same and there was no loss reported or induced. So let's change it up a little bit. We're actually now going to change our network characteristics to be more realistic. Our ISPs are going to vary a little bit. They're never going to necessarily give us the same latency in each direction. And we have to now, deal with jitter and packet loss. So if we look at our WAN simulation console real quick, we can see now that our path characteristics, our latencies in each direction are a little different. The worst being 60 milliseconds, the best being 40 milliseconds. And then on some of our paths, we're inducing a little bit of random packet loss, up to half a percentage point in some cases here. And then again, on each of our paths, we're adding a little bit of a jitter, and we're just varying that randomly as well. So if we would minimize the console here, and we minimize our network diagram, let's look at what the Peplink and the Talari are reporting, starting with the Peplink. So if we look at our path characteristics, the Peplink is reporting the 2 WAN paths at 110 milliseconds round trip and 107 milliseconds round trip. And he's showing occasional packet drops, probably because we're seeing some loss in the network. We're not sending any traffic right now, so that's pretty much in line with what we would expect. Let's just minimize him. And if we look at the Talari view, and enable auto refresh here, we'll notice that because the Talari measures packet quality unidirectionally, we're now able to see the best paths, the latency in each direction, and obviously now pick the best path in each direction to give us, an overall, a slightly better sort of visibility and slightly better granularity as to what's happening on the paths. We'll also notice that we're able to see the variations in jitter. As we can see on this path is reporting about 8 milliseconds of jitter. This path down here is 10, and then some of the paths are 2 milliseconds, and some of the paths are 4, as we can see the variations. We'll also see that we can see the occasional bit of bursty loss on the paths as well. So here, in that time period, we saw a little bit of loss. In this time period, we're seeing a little bit of loss here. This is updating every 5 seconds, and then every so often they will clear up. Okay, so a little bit of a contrast between at least the way we report quality. Let's see how we now use that measurement of quality to steer traffic. Again, our ping is high priority. So on the Talari, we're seeing him pretty much pick the best path in each direction. When we add up the one-way trip times, the latency, and the jitter, we're seeing around about 90 to 95 milliseconds of latency. And I would expect a little bit of variation here because now we're measuring changes in network quality. We actually have to react to that. So not unexpected. We'll do the same test with the Peplink. And, well, right out of the box, we can see with no other traffic, our ping isn't necessarily always finding the best path through the network. We can see it's actually moving around a little bit from 93, 94 milliseconds up to, 120, 125 milliseconds. So not entirely sure why that is the case. We're both prioritizing ICMP traffic to a high priority. We have no other traffic. So right out of the box, I'm not entirely sure why we're seeing that variation. To contrast this, if this was a voice call, that would translate into jitter onto a voice call or a real-time application. So okay, well, not unusual, but let's figure out what's going on here. So let's do our TCP test again. So we'll do the first time we'll do our TCP test with the Talari. Again, we're sending a single TCP flow for 600 seconds. Get him started. Now, we do notice that we see a little bit of increased latency here on the Talari as the load starts to come up. But again, he seems to settle down and seems to still find the best path. But we did see a slight abnormality there in terms of jitter. And we're seeing it maybe a little slower, but we still seem to be finding our best path. Occasionally we're getting a packet jump the hoops there. But our data rate is what we saw previously. We're seeing about 26, 27 megabits of throughput, effective throughput on the TCP flow. If we look at the Talari console and we refresh this, we can see that our traffic is being load balanced for the TCP flow across multiple paths, as we would expect, and everything appears to be functional. Okay, so let's stop that. Let everything normalize. Again, our ping is still unaffected, and now let's repeat the test with the Peplink flow. Again, same test. 600 seconds, single TCP flow. And previously, when all of our WAN paths were the same, we got roughly the same result from the Peplink as we did from the Talari. Now let's see what happens on the Peplink. Give it a few seconds here to ramp up. And right away, we can see that we're not getting anywhere near the same data rate that we were previously when the WAN paths were equal. So in fact, it's extremely low in terms of actual throughput. So we're getting 2 to 3 to 5 megabits of data out of that. Ironically, our ping seems to be unaffected this time. When we were sending 27, 28 megabits on the Peplink in the past, we noticed that our latency got really high for our high priority ICMP traffic. But in this case, because we're nowhere near fully utilizing the WAN links now, our ping seems to be fairly consistent. We're still seeing him jump around from a high jitter point of view, at least jumping around between paths, which would suggest maybe they're using some kind of round robin algorithm. It's not entirely certain. But certainly, we're only getting about 2 megabits of throughput. So you would think at this point in time, we would be just putting this on a single path. But let's go look at what the Peplink is reporting. And we can see that right away, we're sending traffic on both WAN links. But we're not exceeding either WAN link's capacity. We're seeing a lot of packet loss, jitter staying around about the same. So first of all, why load balance an application flow if you can't exceed the WAN bandwidth of that path? So he seems to be generically load balancing the flow. And second of all, why aren't we getting the same kind of data throughput that we were seeing previously? In fact, we're getting nowhere near the performance. This suggests that they don't have very good control over a packet order, and also they're not being very intelligent about how to use the WAN links, because if the link quality is different, they're not able to put everything back together on the receive side. And this is really, very indicative of why Talari's intelligent approach to load balancing and also intelligent approach to measuring one-way network quality is extremely important when we start to look at real networks. Okay, so we're going to stop here, and we're now going to do a slightly different test. So I'm going to do that. I'm going to stop the TCP flow here. We'll just get the ping going here. What we're going to do now is we're just going to induce, with no TCP traffic, we're just going to induce a little bit of variation into our WAN path and see what happens to our ping here. So I'm going to bring up the WAN console. I'm going to move it over here slightly. And I'm going to induce a network event. So I'm going to induce massive packet loss on this WAN link and a little massive packet loss on that WAN link. All right, so now we have some bursty loss on that one. And both seem to be able to react pretty well to that. Let's induce some jitter. So let's induce a big chunk of jitter here. And let's do a little bit of jitter here. Okay. And so now we've changed the jitter characteristics and the loss characteristics in a couple of paths. And the Talari, yeah, we're a little slow, but we're still consistently finding the best path through the network. And the Peplink now seems to be incapable of finding a consistent path through the network. And we're seeing him swing around massively between 92 milliseconds and 100 milliseconds. So again, clearly, he's not always able to see changes in network quality, changes in packet loss, and react appropriately to that. So, and in fact, you can see in the sequence numbers here, we're now missing packets on the Peplink side. If I stop this for a second, and I stop this guy for a second, we'll notice that, you know, we got 399 and then 403. So we lost 4 packets there, whereas the Talari, there isn't a single missing frame from that, because we're able to mitigate the effects of the packet loss by retransmitting the packets, right, or duplicating the packets as needed. So very clearly, obviously, there's a lot more intelligence in the Talari versus the Peplink.